Okay, well, I guess I won't even wait until 5 after since everybody seems to be here. It's my very great pleasure to introduce Andy Berry here for his thesis defense. Thank you all for coming. I'll be short because I know you didn't come to see me, but I want you to know that Andy has been just absolutely amazing to have in the group. We've been working for the last 5 years as a part of a big program with Bill Freeman and others that you'll hear about here, with this goal that we set up when Andy first joined of trying to make airplanes. Well, okay, we basically wanted to do the Forest of Endor scene from Star Wars. That's, that was, in fact, the proposal even was called Endor.tech, and I didn't really use that language for the sponsor, but everybody knew that's what we were trying to do. And we made these sort of ridiculous goals of flying, 15 meters per second through cluttered environments and everything like that, and gave ourselves this 5-year agenda. And I'm happy to say that Andy has actually basically met and exceeded those goals with an incredible amount of work. The other part of the story here is that we teamed up with a bunch of amazing vision people, and throughout the course of the project, they slowly got pulled to Facebook and Google and other things, right? So along the way, Andy started deciding, well, if the vision's going to get done, I'm going to just write the vision algorithm myself. And so he did an incredible amount of work from systems like firmware programming to soldering to building planes, crashing planes. But he also really, I think, challenged the fundamental questions of we had this new problem, which is my camera is moving incredibly quickly through the world, faster than the rest of the world. That sounds like that should make everything hard. Is there any way that makes things easy, right? And he really, I think, hit that head on, and you're going to hear his version of the story there. I also want to tell you that Andy's just become a great friend, and we go on runs all the time. He's the only one that's run all the way to my house with me, and then had dinner with the family and played Candyland with the kids and everything like that. And on those long runs, you get to talk long research talks, but you talk about everything else too. And he's a great guy. I'm sure that's why you're all here. He's got a great view of the field. He's going to go on, and there's no question he's going to do great things at Google, Boston Dynamics next. Anyway, so I'll get off, and I'm very happy and proud to let you hear Andy's spiel.
All right, thanks, Russ. So today I'm going to talk about making small aircraft that look like this, fly through environments that look like this. So in particular, in this thesis, I'm going to do this task with 100% onboard perception, 100% onboard computation, and no prior knowledge of the environment. And I really like this problem because I think it's hard for the right reasons. And what I mean by that is no matter what solution you come up with to flying in these difficult environments, you'll have to solve some fundamental problems. You'll have to do fast, lightweight sensing. You'll have to do fast control integrated with that sensing. And then you'll have to actually show that it works. So people have been working on these kind of UAVs for a while now. And it really started with these big aircraft. So things that look like this. And this is a 94-kilogram helicopter from a 2007 paper. And to put that in context, that's 145 times heavier than the airplane here that I worked on. But these worked really well, right? So they were able to pack a lot of sensing power and a lot of computational power into these systems and avoid things like telephone poles, telephone wires, fly at low altitude at high speed. They worked really well, but they're pretty unwieldy, right? I mean, these are really big machines. So then the field started moving to smaller aircraft, so things that are kind of under 5 kilograms that are a little bit safer. And we first saw it working in motion capture environments. So this is some really well-received work from UPenn doing quadrotors. And this is my master's thesis actually working on flying through small gaps. So these are great, and they're really high-performance systems. But they have this array of cameras around them that's telling the aircraft where all the obstacles are and where it is at all times. So obviously, if you want to move out in the world, you can't have an array of cameras all the time. So then people started working on maps. So you have a known map of the environment, so a predetermined geometry, and then you're flying your aircraft through that. So now your aircraft is sensing the environment, localizing it in a map, and then flying. And then even, so this is some of my lab mate Ani's work, where you're flying in an environment that is not known till runtime. So the aircraft isn't sensing it, but you don't actually know what it is until runtime, and then you got to do the planning really fast. So when I think about these small kind of MAVs, I think there's like two critical things. The first, which I've plotted on the y-axis here, is how much sensing you have integrated into the aircraft. So at the bottom you have motion capture, right? And that's where basically you don't know anything. The aircraft itself doesn't know anything about the environment, right? And at the top you have a full 3D onboard sensor, so you're sensing the whole environment. And on the x-axis I've plotted speed. So all these systems are about the same size, same weight. So obviously going faster has a lot of advantages. So, and the numbers here are in chronological order. So you can see people worked on this motion capture stuff at a variety of speeds first, and then there's been a focus on these 3D onboard systems. And my thesis is going to do 3D onboard sensing at really high speeds. So all of these papers, all of these systems have planning and control underneath them. And I want to talk about that a little bit. So folks have done differential flatness, which allows you to do planning and building out trajectories very quickly for nice models of quadrotors and et cetera. Then there's nonlinear model predictive control has worked pretty well. There's some computational problems that I think are still being solved there, but it has worked well. In this talk, I'm going to speak about trajectory libraries a fair amount. And trajectory libraries aren't my idea. They're not a new idea. They've actually worked pretty well for a while. And then almost all of these systems have some kind of LQR controller running on the bottom. And I'm going to use that as well, so I'll talk about that. On the sensing side, you can first start with non-visual sensors, so something like a LiDAR. So this is a system where you have a laser, you shoot a beam out, and it measures the distance to an obstacle. And these work really well for localizing in a map. And that's primarily because the LiDARs you can buy right now are 2D. And if you want to put a 3D LiDAR on one of these small UAVs, it's pretty tough. They're just starting to come down to the size and weight where you can really fit one on these small things, but they're not quite there yet. There's also Connect. So these are like the active IR sensors, and they work awesome for indoors. You get like really pretty high frame rate pictures, but they don't work very well outdoors because the infrared is blinded by the sun. On the vision side, there's monocular vision. So this is some work from CMU doing monocular vision. So you have a single camera image, and you're trying to estimate depth and then do control based on that. And this is working off-board. So you're streaming the images off because that's not quite fast enough yet to put on board, although I think we're definitely going to see that soon. And then the second video here, I just love this work. So the idea here is you take the optical mice sensor, like for an optical mouse, like you'd plug into your USB port, you put a different lens on it, and then you can get pretty general optical flow ideas. So you can say like there is an obstacle to my left, there is an obstacle to my right. You get that at a really high rate, like 4.5 kilohertz, really fast. But what you can't do is describe the geometry of the scene and try to like dodge under a branch or something. On the stereo vision side, so people have been doing stereo for a long time on these kind of aircraft, but the problem has always been that stereo vision is generally just too slow for fast flight. So a lot of folks have worked on that. So there's GPU stereo, and we're just starting to see the GPUs getting small enough for these kind of aircraft. And then there's FPGA stereo. So this is the idea here is you take a dedicated chip that isn't a CPU, it's just going to clock through stereo, so it can do it really fast. And we're starting to see that be put on these kind of aircraft as well. All right, so what is my thesis going to talk about? I'm going to talk about three things. First, a novel stereo vision algorithm for really fast obstacle detection. Second, control algorithms that take the data from the stereo system and avoid obstacles. And third, I'm going to show a demonstration platform of the system working. All right, so let's talk about stereo vision. Right, so everybody, when you do stereo, you always start with this. So this is two camera images, and they're slightly different. And they're slightly different because the cameras are spaced apart. And your goal here is to take the differences between these two images and compute depth. And in particular, the way you do that is you do a whole bunch of calibration and rectification beforehand. And what that buys you is that an obstacle in one row of the left image will appear in the same row in the right image. And then online, what you do is you search. So you pick a spot here in the left image, and then you pick a spot in the right image, and that corresponds to a depth. And you say, do these match? Right? And you say, okay, well, maybe they do, maybe they don't. And then you sweep through depth, moving this block in the right image. And what that allows you to do is you pick the best one, and that tells you the depth at that block. And then you're done with that block, and you move on. So there, and you have to do that same sweep again, and that's basically block matching stereo. The problem is that takes a long time. So these are the kind of computers that we actually run on the aircraft. And if you go put that kind of stereo vision system on that computer, it's going to run at 5 to 10 frames a second. To give you an idea, so our aircraft is flying pretty fast. So if you're running at 10 frames a second, you're going to move 1.2 meters between frames. And that's really scary if you're a control theorist, right? If we can get up to 120 frames a second, now you're moving a lot less, like 0.1 meters, right? So that's much more reasonable. So the idea is we want to do it fast. So I had this idea. What if we don't do that search? So I'm going to ask a different question. Is this pixel block 10 meters away? And what does that look like? So we have the same picture as before, right? But now I'm only going to look at 10 meters away. So I immediately map to a spot in the right image, and I just check. Does it match? Does it not match? Then I'm done with this pixel block over here, and I can move on and I do this search. And this is the picture I want you to have in your head. So you have some detection region, right? You have no idea what's closer to you and no idea what's further away. But you're an airplane, and you're flying forward, so you can remember what you saw and build up a full 3D map of the environment. And really the reason this works is that the aircraft is moving faster than almost anything else in the environment. So the environment's not going to change very much while you're flying. So okay, so that sounds great, right? You go ahead and you put it all together, and it turns out you have to deal with this problem called visual horizontal invariance. So the trouble is, what if I have two things that look really similar in the same row? And remember, these are really local features. This is a 5 by 5 pixel block, right? We're looking at 25 pixels. Turns out, this is exactly what the horizon looks like. So you can't tell if it matches, right? So without some kind of higher level system, it's pretty difficult to deal with this disambiguity. So I'm actually not going to solve that problem. What I'm going to do is I'm going to detect it. So I'm going to filter for visual horizontal invariance and get rid of them. And the trick is they have another match nearby, right? That's their fundamental property. So what I can do is whenever I find a match, I can search at another depth. In this case, I'm going to search at really far away, which is the horizon, right? And I'm going to check. Do these have a second match? And then I'm going to throw it out if they do. And in practice, you move it around a little bit because your calibration is not perfect. This is what it looks like. So you can see here the boxes are detections. And you see we some detections on the horizon and then some detections on this horizontal obstacle. When you turn the filter on, you lose them both, right? Because I can't solve that ambiguity, right? So I can't disambiguate that. But that's OK, because it turns out most trees in the world are not made up of solely horizontal members, right? So I'm just going to give up searching for horizontal members and assume that I'm going to see enough of the other obstacles. OK, so you go ahead and run that. You put it on this computer, and we can run it 120 frames a second on board the aircraft on these small computers. So great. So before I show you any flight video, I have to say all of our flights have an onboard safety tether. So this is what it looks like in practice. So the blue boxes here are in-frame detections. And then the red boxes say, I saw an obstacle here in the past, and I'm showing you where it is. And I'll let the video play again. All right, so it seems like it's working, right? But we want some numbers. So what I did was I took the aircraft and I walked around with it. And in this case, this is running at 5 meters. And I collected a whole bunch of data, and then I did some benchmarking. So the way I decided to do the benchmarking was to run a stereo system offline. So I took OpenCV's block matching stereo, and I'm going to use that as a proxy for ground truth. So I'm going to walk around, collect a whole bunch of data, and then I'm going to run them both on the same data set, and then I'm going to compute this number. So here the white boxes are OpenCV stereo, that's our proxy for ground truth, and the red boxes are Pushbroom stereo. And what I'm going to compute are all these distances, right? And in particular, I'm looking for distances that are very large, because that indicates a false positive, right? That's a place where our proxy for ground truth said there is no obstacle, and Pushbroom stereo said I found an obstacle. Right? So if you go ahead and run those numbers on all of the walking data set and some flight data, this is what you get. So within 1 meter of ground truth, you have 71% of Pushbroom pixels, and then 2 meters we get to 81%. So it turns out this is definitely sufficient for obstacle avoidance. So that's the false positive benchmark. What about the false negative? This is actually worse, right? So you want to make sure this doesn't happen. So again, white boxes here are our proxy for ground truth, OpenCV, and red boxes are Pushbroom, right? And what you don't want is that OpenCV says there's a tree here, and Pushbroom says no, there isn't, right? Because then you'll hit the tree, right? So that's really bad. So again, I'm going to compute these numbers, right? So I'm going to take every ground truth pixel and compute the distance to the nearest Pushbroom pixel. And this is what that looks like. So there is a Pushbroom pixel within a 1 meter ball around OpenCV stereo 67% of the time, and then within a 2 meter ball 91% of the time. All right, so maybe I've convinced you that this is worth putting on an airplane. But to show you that video, I had to do two things, right? I had to do stereo detection, and then I also had to do state estimation. Because when I remember what I've seen, right, I need to remember how I've moved to update that estimate. So in this work, everything is GPS denied. And the idea here is that even though our airplane actually has a GPS on it for debugging, if I get a GPS drop, I don't want to all of a sudden start slamming into things, right? So everything's GPS denied. And our strategy here is we're going to start with an open source state estimator, which actually came out of Nick Roy's group. And then we're going to add an input for a barometric altimeter. So this is a tiny chip. The chip is like that big. And it has surprising resolution, actually. So it can get maybe 1 to 2 feet resolution using just air pressure. So that'll give us a good idea of our altitude. Then we're going to also add a pitot tube airspeed sensor. So on our airplane, you can see this is the pitot tube right here. And those are pretty standard aircraft sensors. So any airplane you've ever flown on definitely has a pitot tube. So you add those two things, and what that gives you is pretty good estimation of altitude, roll, pitch, yaw, forward speed, climb rate, angular rates. But you have a limited ability to estimate x and y position, right? You don't have GPS, and you don't have any external reference. Right? And it turns out that's OK. So because Pushbroom stereo only needs relative position, and it only needs it until you catch up to the obstacle, so it only needs it for about 1 to 2 seconds, it's OK to have an estimator that isn't perfect for x and y position. All right. So now I want to show you our state estimation working. But remember, I'm outside, right? And I'm flying at 20 to 30 miles an hour. So I don't have a motion capture system to give me ground truth. So I'm going to make a different argument, which is that I do have a camera. And then I'm going to plot all of our state estimates on top of it and show you that it at least looks reasonable. So over here on the left, that's our airspeed. On the right is our altitude. And then this is our pitch and roll. So this is an artificial horizon. The yaw is down here. And you can see this is what it looks like in flight. So we have decent state estimates, pretty good tracking. This is all manual flight. So, OK. All right. So now I've given you a pretty good idea of how we're going to do sensing on the aircraft. And I've shown that using only onboard sensors, I can do a pretty good state estimate. So that's our sensing plan. What about our control plan? I'm going to use trajectory libraries for control. And I'm going to use LQR feedback. All right, so let's talk about trajectory libraries. So what's the plan here? Right, I have some airplane, and I have a plan about where I can go. Right, so I've pre-computed a bunch of options. I can turn left, I can turn right, I can go up. And then online, I'm going to choose which one of those options to execute. Right, and this isn't actually a very new idea. People have been doing this for a long time with pretty good success. So, but before I can tell you about a trajectory library, we have to talk about how to build just one trajectory. Right? So I'm going to take a model-based approach. And the reason I want to do model-based approach is that it's going to allow me to do optimization for trim conditions, trajectories, maybe even controllers. Easy conversion to other airframes. Right? So if you decide you don't like my plane, you want to put it on your plane, if you put a new model in, everything else will work. And then maybe we could even do safety verification. And I'm going to talk about that in the related works, in the future works, for safety verification. OK, so this is what my model is going to look like. So I have a nonlinear model. This is my state vector x. It's got 12 states. So x, y, z positions roll, pitch, yaw, and then the time derivative of all of those. So those are my velocities. My control vector u with 3 inputs, right? And that's my left control surface, right control surface, and then the throttle. All right, so, but everything that's really exciting is happening in F, right? So X is my state, U is my control, and I'm going to use flat plate dynamics. So this is what you might think my model ought to look like, right? But if I were going to do that, then I would have to do a bunch of computational fluid dynamics, and that's going to be really hard and really slow. So I'm going to take an approximation that looks like this. So this is 5 flat plates, and it turns out, it's kind of surprising, this is actually good enough. So I'm going to do the aerodynamics from 5 flat plates. I'm going to put that all into F, and then I'm going to build a model. So there's a lot of details that go from this picture and that equation to an actual good, working, identified dynamic model of the aircraft. But I don't have time to talk about that today, so you're welcome to read the thesis. That's all in there. So let's assume now that I have a good dynamic model of the aircraft. Now, what do you want to do first? Usually, the first thing you want to do is fly straight and level, right? OK, so how are we going to do that? Well, it turns out, so that if you look at our state vector, right? This is our state vector. And in fact, if you look at the time derivative of our state vector, the last 6 numbers are accelerations. OK, so if you're flying straight and level, all your accelerations are 0, right? So I can actually set that up as a feasibility problem. I can search over a state and an input that sets all of the accelerations to 0 in my model, and then I make sure I don't give it more throttle than I'm allowed to, right? And I can actually solve that problem really quickly. And that'll give me an x naught and a u naught, which is the state I want to be in, right? But that's not quite enough, because what if I get hit by a wind gust, right? I need to know how to get back to that state. Now, that's my goal. How do I get back there? And for that, I'm going to use pretty standard nonlinear control techniques. So I'm going to take the error. So x bar is going to be my error here. And then I'm going to compute u bar. And the way I'm going to do this is I'm going to linearize my model around x naught and u naught. So I'm just going to take a Taylor approximation around x naught and u naught. And that's going to give me a linear model. It's only locally valid, right? But with a linear model, that's great. I can use 100 years of awesome control theory and make that work. So I'm going to put LQR on this. And this is what it looks like in practice. So for this video, I want you to watch up here. So this is manual. I'm going to flip the plane upside down. And then I'm going to turn it to auto mode. And you'll see it stabilized. So this is stabilization from inverted flight. All right, so another thing that's really awesome about model-based control, I can change one number, right? I'm going to change z dot, which is my climb rate. I'm going to set it greater than 0. I can solve the whole thing again, right? And now I have autonomous takeoff. So I'm going to throw the plane in this video. And it's just going to fly away. Right? And the point of this right here is right here, right? No hands. So I'm not flying. All right, but what about something like this? Right? This is not a trim condition. Right? The aircraft is experiencing substantial acceleration at that point in time. So I need another plan for that. Right? Okay, and there's really 2 options I'm going to explore. And the first is basically replaying of flights. So I fly the airplane manually. I remember what I did. I put a stabilization controller around that. And we go ahead, and you can just replay that. That could be a trajectory. So I did that in the thesis, and then we can also do trajectory optimization, where I take my model, I build a trajectory using my model, and then I can stabilize that and run them online. I did them both here in this thesis, and I want to show you what the first one looks like. So now we've got these boxes, and these boxes are showing you a visualization of what we're trying to fly. So you can see this is a left jog, and this is actually a trajectory we used in the avoidance maneuvers. So for trajectory optimization, what is our goal? Our goal here is to take our model and optimize over a state and an input tape to find an open loop trajectory, right? And then we're going to go ahead and stabilize that using similar techniques as before. So what that looks like in practice is something like this. So this is a simulation. In this case, I've told the aircraft you have to be at 90 degrees halfway through the flight. So it's basically a knife edge maneuver. And then you can put a stabilizing controller on that and fly that on board. So this is what that looks like in the air. So we can take a look at the tracking. Now remember, we don't have ground truth, so this is all based on the state estimator. And in this case, the black vertical lines here are the beginnings and ends of the trajectory. So this is X, Y, and Z, and you can see we lose a little bit of altitude, about the amount we expected, which is not surprising, right? You roll the aircraft over, you've lost a lifting surface. This is our roll, pitch, and yaw. So you can see we're rolling up to about 100 degrees, so pretty substantial roll there. And then these are the control actions for the left and right elevons. So the thing here that's interesting is the difference between the actual and planned is what the feedback controller is actually doing, right? That's the stabilization system that's accounting for model error and for any disturbances experienced online. Okay, so now I've argued we have a decent plan for sensing. I've shown that I can do some kind of control. What about online planning, right? I have to decide what trajectory to execute online. And to do that, I'm going to use a pretty simple system. I'm going to first ask, is my trajectory in collision? Right? So I'm flying straight, and I'm just going to keep asking the stereo system, are we going to hit anything? And the moment that it says yes, we got to do something, right? So I'm going to look through every trajectory in my library, and I'm going to ask these questions. I'm going to compute the distance between that trajectory and the point cloud, right? I'm going to reject all trajectories that hit the ground, and then I'm going to execute the trajectory with the maximum distance to the point cloud. So this is a pretty simple algorithm, and we can definitely do better than this. But it turns out this algorithm allows you to check the entire library. In this case, this is for a pretty small library, 7 trajectories, in under 20 milliseconds. And we can take a control action half a millisecond after that. OK. So now I want to talk about experiments. So the experiment I want to do is I'm going to take off from a catapult launcher. You have to do some stuff to clear the cable, otherwise you get tangled up in it. I'm going to climb to a specified altitude, and then I'm going to avoid obstacles. At some point, the safety pilot's going to take over and land the aircraft. So this is what our launcher looks like. So it's a couple pieces of PVC with a bungee cable. This is what an autonomous launch looks like. So all I'm doing here is I'm pressing a foot pedal that's down there. And the aircraft flies away. This is what it looks like from the onboard right camera. So altitude's going up. That's a good thing. All right, so now this is autonomous obstacle avoidance. So you put the whole system together. So you can see here the red boxes are the detections. This is played at 1x. And this is what it looks like if you're a tree, if you're a camera on a tree. And then this is quarter speed. So you can see the red boxes are the detections. We fly under the dogger pillar, and then we keep going straight. So I'll let that video play again. And here's the trajectory library we used in that flight. So you can see a lot of our trajectories are trim conditions, and then we have these more dynamic maneuvers, which we definitely execute down here. This is what it looks like in a 3D visualizer. So you'll see the red boxes coming up are the obstacle detections, and then you can see the planning system execute. This is what the tracking looks like. So this is X, Y, and Z tracking. You can see, again, the black vertical lines are the changes of trajectory, right? So you can see there's a lot of things going on right here. We're changing a lot of trajectories there. And I think actually more interesting is roll, pitch, and yaw. So we have pretty substantial roll here, right? And then you can see sometime later, we have a dramatic and permanent change in our yaw angle, right? And that's our obstacle avoidance maneuver. That's when we avoided the obstacle. All right, so here's another example of avoiding the same tree. And then some more. So these are all played at 1x. So we're going about 25, 26 miles an hour here. So then if you have a really nice lab mate who's standing over there, you can get him to fly a plane behind you and take some videos that look like this. So that's an autonomous maneuver avoiding that tree. And then here's another one. And this is the onboard. OK, so over 16 successful obstacle avoidance flights, we flew 1.5 kilometers autonomously, almost 8,000 stereo matches. We executed over 150 trajectories average speed of about 27 miles an hour. This is a plot of the coverage of trajectories. So what this shows you is that in our library, we're executing all of our trajectories. There's no trajectory that's being left out, and unsurprisingly, level flight is the most common. So we did this really over 3 environments. The first is a pole in the middle of an empty field, right? So this is a 15-foot tall pole. I put a GoPro on the top. Nothing else, right? The second environment is 2 trees. So the airplane is flying between or around these 2 trees. And then the third environment, the same 2 trees, but at a different angle, which gives you a bunch of obstacles here, and then there's these extra trees behind you. So this is what our failure rates look like. So the first 2 are great. And then our strategy of push the aircraft until it fails paid off. And I want to talk about why some of the failures happen, because I think it's a pretty interesting thing. So it turns out they were split between vision and control equally. And let's talk about vision first. So in one case, the vision system failed to see the obstacle. And I'll talk about that in a moment. In 2 other cases, we had poor calibration. So what that means is you go look at the video and you look at the stereo calibration, you can tell it's far off. So you would never expect to have success there. And in 2 of the cases, we don't have any video. And that's due to technical reasons. Basically, if the aircraft loses power because it's in a collision, you can't dump all the video from the RAM to disk fast enough, so you lose the video. So we know that it was a vision failure, but we don't know why. All right, so let's talk about the first one, where you fail to see the obstacle. This is the video. So there's 2 things that are happening here. One, you have a gray sky against gray leaves. So you have a really low contrast. And it doesn't necessarily look super low here, but remember, you're searching on a 5 by 5 pixel block level. So it's very small contrast there. And the second thing that happens is we actually succeeded avoiding the first tree. And then the second tree, we're actually pitched down. So it's a little hard to tell, but during that critical point, right, where you're 10 meters away, you might actually not be looking at the tree. So this is a tough one. But that's why we failed to see it in that case. For the control failures, I think these are actually really interesting. So we had 2 cases where we had an insufficiently rich maneuver library. And what do I mean by that? What I mean is that, say the aircraft is flying at a brick wall, right? Your only option is to turn really aggressively, like take a 90-degree turn, right? Well, I don't have a 90-degree turn in our trajectory library. So my airplane is always going to try to fly through the brick wall. So this is what that looks like. So you see the vision system's great. The vision system says this is a bad idea. But the control system tries to go through, right? And we actually almost made it. The second interesting thing that happened here is that our trajectories only start at level flight. So this causes a really interesting failure mode. When the aircraft is already rolled, and then you choose to turn in the direction you are already rolled, you'll crash. And let me give you an example. So I'm going to start the aircraft rolled to the left. I'm going to choose to execute a left turn, right? What is the first control action I take? My aircraft is rolled to the left. My trajectory says I want to be level. The first control action is a hard right roll to bring my aircraft level, which is the exact wrong thing to do, right? And this is what that looks like in practice. You can see we're planning to go left, and the aircraft actually rolls to the right. So this is a fundamental problem. It's a solvable problem, and I'll talk about that in a bit. But it's a fundamental problem with our system. In this particular case, we actually did OK. So the planning system took over, decided to climb. We actually hit the obstacle, but kept flying and eventually landed. So Pete is an amazing chase cam pilot and actually caught it on video. So that's what that looks like. So this is the roll plot. So you can see we start rolled, right? And then our plan and our reality are totally different, right? And then, of course, we hit the obstacle here. This is our yaw plot, right? Well, we should have yawed here, right? But we didn't. And then we hit the obstacle. We end up with about a 74-degree yaw that we recover from. So I think it's actually most clear. This is the plot of the left control surface deflection, right? You can see our plan is to deflect the left control surface up. Right, that'll cause a left turn. And instead, we very aggressively deflect it down. Right, so that was a mistake. All right. So how can we improve that, right? Well, the first thing we can do is we can have multiple starting states in our trajectory library, right? So I can say, if you're already rolled, go use this other trajectory library that starts with the trajectories that are already rolled. And in fact, the computational cost of that is pretty low, because the high computational cost comes from comparing your library to the stereo system. So if you can just pre-select your library based on your initial condition, that actually doesn't have high cost. But we can do better than that. And this is Ani. He's somewhere. Where are you, Ani? There he is, over there. So Ani has this really awesome system where he has verified funnels. So the idea here is that I'm flying my aircraft, and I say I want to execute a new trajectory. What Ani's system will allow you to do is say, this is the set of trajectories that are safe to execute. So they will avoid all the obstacles and accept the initial condition you're already in. So we have good ideas for how to do better there. All right, what about wind? Right. So all of these things we flew on mostly not windy days, not perfectly. Well, there's some really interesting onboard wind sensing work. So you'll have to ask Bill about this. I don't think this is going to happen next year, but there's some potential, I think, in the next decade to see some really cool onboard wind sensing. And then our group has actually also done some control through wind. So we have interesting ideas there. All right, what about the stereo system? So there's some obvious improvements we can do with just a little bit more computational power. Right, so we can search at multiple depths. Right, so right now I'm only searching at 10 meters away. Right, what if I searched at 10 meters and 8 meters away? Well, then I could check for false positives. Right, so I could see, did I see it at 10 and 8? Right, I could track obstacles. I could even check along a planned trajectory. Right, so it turns out there's some issues with occlusions there. But that would be pretty neat, right? This is the trajectory I'm planning to fly, and I'm going to just always check along that trajectory and see if I'm in collision. Also, the GPU implementation. So the folks that sell this board just came out with a new board that has OpenCL in the same form factor. And Pushbroom Stereo there's no reason you couldn't do this even faster in GPU. All right. So our goal at the end of the day is to make these small aircraft fly in clutter. And we want to fly fast, we want to be really safe, and we want to have good, deep integration of our vision system. But flight experiments are expensive, right? So our group is thinking about this idea right now. Can we build models that include vision and control, right? And this would reduce the amount of time I have to drive to a farm to fly these planes, right? So if we can build vision and control models, so that's modeling robotic vision, then we could systematically find and correct failure modes for the vision system, the control system, and the integrated closed loop system. Now, I think we have good answers for how to do this kind of stuff with control right now. I think there's a lot more to do on how can we simulate these closed loop systems with vision in the loop. I think it's a really exciting field of opportunity there. All right, so my thesis presents Pushbroom Stereo for high-speed obstacle detection, control algorithms that integrate Pushbroom Stereo in the loop, and then I demonstrate the fastest MAV flying in complex obstacle fields with only onboard computation and sensing to date. So everything is open source, so you're welcome to go download all the code there. And our entire lab simulation environment is open source as well. So a huge number of people helped me. A lot of you guys are here today. So I want to thank Russ for a lot of long runs. And the committee, Bill and Nick, for reading the whole thesis. Thank you. And then there's just so many people that have helped me. So Ani and Pete and John are amazing pilots. They took a lot of the video that you saw. All the folks who I've worked with here, the support CSAIL's given me, and then, of course, East Campus for giving me a home for 4 years. And then my mom, dad, Jenny, and, of course, Katya. So thank you. I'll take questions now.
So just to tell you the protocol, the floor is yours. You guys get to just fire questions at it. After that, we'll ask people who aren't on the faculty to leave, and the faculty will fire harder questions. Even if you guys get all the good questions out. And then, assuming things go well, we'll ask you all to come and help us celebrate kind of in 3280. But please fire away.
Yep.
Do you have a chance to test this indoors?
Yeah, you need a really big building. So the answer is no. The plane flies at 30 miles an hour. So we looked at a lot of different very large buildings. We didn't find one. Yeah.
So I think you had it in your slides, but what kind of onboard computer were you using, and how much load were you putting on the system with all your reception and control integrated?
Good question. So we have two of these computers. These are the Odroids. So it's a quad-core 1.7 gigahertz ARM with 2 gigs of RAM. So two of those. And the load is 100%. Yeah.
The max distance that you could detect disparity in your stereo image?
Great question. So that's limited by a couple things. It's limited by the baseline of your cameras. It's limited by the resolution, and also the lenses you choose. So if you choose really wide-angle lenses, you get effectively less resolution. In this case, 10 meters is about as far as you can reliably detect. At 10 meters, you have about 3 pixels difference between an object and effectively infinity, where you don't know. You can change that by picking a different baseline, picking different lenses, picking different cameras. We picked this baseline because there's a carbon fiber rod that runs inside the aircraft right next to those cameras, so you get a stiff mount. Yep.
I have a calibration question.
Yes.
How much calibration did you have to do before each run? And did you find that the dynamics of flight were actually torquing the base mounts for the camera enough that you had to recalibrate?
That's a great question. Yeah, so I was really worried about that. So you have to do a full calibration at the beginning. And then in practice, we would calibrate probably once every 4 or 5 runs. And you saw we had some issues with calibration. So doing online calibration would help a lot. The cameras are also not mounted particularly rigidly. They're dug into the foam, which actually works surprisingly well. So the dynamics of flight, not a problem at all. Hitting stuff, even landing this plane is kind of a controlled crash, and you definitely have some problems there. Yep.
For the motion primitives, did you take into account the model of the airplane, and if so, how accurate was that model?
Yeah, so the question is, for the motion primitives, can I comment on the model? Is that right? Yeah, so the model is not completely accurate. And if you look at some of our groups of work, there has been other work in taking flat plate models and tuning them to be more accurate. The primary problem with getting a really accurate model of this system is you don't have motion capture. So you're trying to base your model on a state estimate that isn't great. So there's a fair amount of work you have to do and things you lose since you only have the state estimate. It's good, but I wouldn't say it's the best model we've produced by any means. Yep.
So you're talking about switching libraries if you were starting from different initial conditions. Would you
Yeah.
think that you would need various libraries closer to different sets of initial conditions?
Sure.
Can you think of any other kind of cheap ways that you could probably implement on this sort of system, trying to smooth trajectories together, or push where you're starting from that trajectory from that initial condition or something like that?
Yeah, sure. So the question is, when we're switching trajectories, how can we do better other than just creating a whole bunch of different libraries? My answers are yes, we can definitely smooth. So right now we're smoothing effectively with an LQR controller, right? But you can do a lot better if you can reason about switching not always at the beginning of a trajectory, you could do better. So that would have saved us in the case I showed, right? Because if you say, oh, well, this trajectory has a state that's closest to us half a second into it, then you could just jump to that and execute that, and you might do better as well. But there's computational cost to that as well. Yeah?
Did you ever think about other visual algorithms you could use to augment the Pushbroom stereo?
Absolutely, yeah. I think, so the question is, are there other algorithms you could use to augment Pushbroom stereo? Yes, I would love to do that. But we literally have no computation left. So we're processing frames at 8.3 milliseconds a frame. And I did every optimization I knew how to do to fit that on the processor. So I think
What algorithms would you use if you had more
Yeah, sure. I think visual odometry would allow you to estimate wind, which would be awesome. Right? So right now, we're just blind to wind. We assume the wind is 0. So if you had some kind of ground reference to do that, that'd be great. And then there's a lot of different obstacle detection algorithms or depth algorithms that you might look at. I mean, certainly monocular, you would love to do if you could. Yep.
Curious about methods like this. How well would it do if you're flying through a dense and deep environment with lots of obstacles and you had to sort of limited observation horizon?
Yeah, so the primary problem is that occlusions will get you, right? Especially if you are turning. I mean, you can only see at 10 meters, right? So super dense environments, you have to account for that. And if you're flying slower or you're on a ground robot and you're moving slower, you definitely could check different disparities to allow you to kind of compensate for that. Maybe you could say, oh, we just turned a bunch, so I'm going to start checking at 2 meters and then push that out, right? And you can tune that knob based on your computer. But yeah, there's clear problems where if you turn 90 degrees, you just don't know. Right? Yeah.
How did you come up with the Pushbroom stereo idea?
How did I come up with Pushbroom stereo? Well, so we thought a lot about it, and really what happened was I read about stereo vision, and a lot of people, so when I give the talk, I talk about that search as a search through depth, and that was an insight I had as I understood stereo vision, and then once you kind of see that, then it's a little bit easier to see Pushbroom stereo. But I was walking up the stairs in East Campus one day when I figured it out. Yeah.
You talked about integrating vision into the controls modeling system. Do you think there's room for integrating vision and whatever your other senses are into the trajectory design?
Ooh, can you integrate vision into trajectory design? So you definitely can think about having systems where you're thinking about what you're seeing, right? And Nick's group actually does a fair amount of that, where you say, oh, I'm going to be careful about turning 90 degrees really fast because then I'll be blind, right? So you could do something like that. Other than that, I don't know. That'd be interesting.
Oh, is this? Sorry. Oh, I see. I was wondering where that was. I'm being recorded, but also. Okay, awesome.
How rude. Yeah.
Did you try avoiding or removing UAVs?
We tried avoiding other moving UAVs. No, and the primary reason there is it's really hard to get 2 UAVs flying at 30 miles an hour to get anywhere near each other. Yeah, taking the chase cam shots was really, really difficult. So.
Then your algorithm will work with moving obstacles?
So there's fundamental issues there you have to think about, right? Whereas you're only going to detect at 10 meters, and if the obstacle is moving and you're not going to see it again, you could try to do multiple detections and then do some kind of modeling where you estimate its velocity. That certainly could be reasonable. But yeah, if something's moving really fast, faster than you're going to have to be really careful.
What's like a peak English rates you're getting? Like, was there any problem with blurring or anything like that?
Great question. Peak angular rate. So the aircraft has a maximum roll rate of about 300 degrees per second. At 120 frames a second, we never saw any blurring effectively. You might see it in one frame as the catapult launches, and you'll definitely see it, if you slam into a branch or something. So, sorry, it's 300 degrees per second roll rate. Yeah, 2,000 would be very impressive. Yeah. We certainly have lots of video. I think none of our trajectories in the library would actually hit that rate. But I showed you one where the aircraft did a max roll, and that's easy to do. You just push the stick all the way over. It's amazing to me how many problems go away when your frames are really fast. I was really surprised.
You don't think to make it more dexterous or more agile, is it improving the frame rate or improving the model?
In this particular case, I think improving the model would help the most. 120 frames a second seems to be very good. There's actually a paper that argues based on ray traced simulated vision that you get diminishing returns past about 100 frames a second for whatever their environment was. If I was going to do anything, I would fix the model and improve it more. All right, one more.
Could this be changed to use more structure for motion concept on a monocular camera?
That is an interesting question. Yeah, could you do structure from motion? Yeah, I don't actually know that literature well enough to be able to answer that. I think that there's definitely potential there, right? Because you effectively have a stereo view, and you're going to have to do the same kind of search. And especially with an IMU, you might be able to do pretty well. That's something to think about. I don't know. Oh.
Why trees, and would something that's easier to see result in a more reliable flight pattern? It seems like something like buildings or like skyscrapers would be much easier to fly.
Sure. Yeah, so the question is why trees? And the answer is because Russ wanted to do the Forest of Endor. But in reality, if you look at the kinds of things MAVs are avoiding, trees and buildings are definitely useful. Buildings tend to actually have pretty high contrast, and a lot of vision is about contrast. So I think buildings might actually be easier, especially on their edges.
So this is a question about your experiment design.
Sure.
You tested your approach and basically forest environment, a bunch of trees. And one of the limiting things to your approach is like having a second obstacle that you need to avoid, which you cannot see or anticipate when you're doing the first avoid.
Sure.
Right. So within your approach, considering the design of the plane, your models, and your algorithms, what is the minimum distance between those two obstacles that you can successfully avoid the two of them?
That's a good question. Yeah, and so I did show one example where that exact thing might have caused a crash. Yeah, so the trees in this example were pretty far spaced out, maybe 20 meters at 20 or 30 at the longest, and 10 probably at the shortest. I don't actually know. Well, I'd have to think about that to understand what the limiting factor would be. Because if they're really close together, right, you'll actually see it before you make a maneuver. So there's probably some dead zone there in the middle where you haven't recovered from your maneuver yet, and then you hit the tree.
Okay, let's thank Andy again.